Okay, so here is the mock quiz. Again, I'm re-recording this due to some problems, but no worries. So for the first problem, we're going to be looking at two half reactions, and it's basically asking which one is the reducing agent. Okay, so that means which one is undergoing oxidation. It's undergoing oxidation, so it's the reducing agent. So if I see here, the first thing I want to do is label the anode and cathode. That kind of helps. So the anode is the one with the lowest SRP. Okay, these are the SRPs. And sorry about the noise in the background, but the lowest SRP here is this one. Okay, so this is going to be the anode. And like I was saying in the review session, the anode undergoes oxidation. And the cathode up here undergoes reduction, okay? So what's really going to happen here is this SN is going to go from its solid form into its aqueous ionic form. Okay, so already we know that the one that's being oxidized is this SN here. That is going to be the reducing agent, okay? And it's not going to be any of the products here, right? It's not going to be SN2 plus, that's a product. And it's not going to be the Fe here. The products are never going to be the agents, okay? We're only looking at the reactants. Okay, so for the next one, this one is asking which one is going to be the anode, the electrode at the anode. Okay, and similarly, we just need to figure out which one has the lowest SRP. And so in this case, it's going to be this one. And so if we just flip this reaction, this is the one that's going to be oxidized, and that is going to be the solid over there at the anode. We always look at the lowest SRP to tell us which one is going to be the anode. Okay, so now we're going to be looking at a few conceptual problems. And so the first one is saying, and we just have to label which one is true. So the first one is saying delta G non-standard is never equal to 0 when the system reaches equilibrium. Okay, so this is going to be false because delta G non-standard can't really tell us about equilibrium directly, right? Only delta G standard can tell us directly about equilibrium. So that's why we can't trust the first one. The next one is saying delta G standard is more negative when there are more reactants added to the reaction, okay? So this is kind of like, this is a trick question because if this was delta G non-standard, then 100% this would be true. So if we added more reactants and we drove the reaction more forward, delta G would be more spontaneous. Delta G would be more negative. However, this is saying delta G standard. And so it's a little tricky because at delta G standard, we can't really touch the standard conditions, okay? Delta G standard is only going to have 1 molar of every reactant or product in our system. And so that's why this one is going to be false, actually. However, if this was delta G non-standard, that would be true, okay? The next one is saying at standard conditions, delta G non-standard and delta G have the same value. And this is true, okay? Because at this point, they have the same conditions, and that's why they're going to have the same value. I know it could be a little bit confusing. Just imagine delta G standard is just delta G at a specific kind of condition. They have, specific environments, like concentrations and things like that. And if we bring delta G non-standard to a standard condition, they're the same thing, So don't overthink it. The next one is saying if reactants are favored at equilibrium, delta G non-standard will be positive at all points during the reaction. And similarly to the first statement we were saying, at equilibrium, we can't really tell with delta G non-standard, right? We need to really reference delta G standard. If we're going to be asked any questions about equilibrium, we need to look at delta G standard, not delta G non-standard. However, if this was delta G standard, then it would be true. If reactants are favored at equilibrium, for example, if there's a K constant, equilibrium constant less than 1, reactants are favored at equilibrium rather than the products, then it would be positive, okay? But this is talking about delta G non-standard, that's why it's false. Okay, so for E, delta G and delta G are temperature independent. So this is false because they're very dependent on temperature. Okay, we see temperature in every delta G equation we use, so it's very important. The next one is saying delta S of the surroundings and of the reaction will not always have opposite signs, and that's true. There's nothing keeping them having opposite signs. For example, delta S of the universe equals delta S of the surroundings plus delta S of the system. It doesn't necessarily mean that they'll have opposite signs, okay? The next one is saying delta G or delta G standard is negative when spontaneous, and that is always true. The next one is saying enthalpy represents free energy to do work in a reaction, and this is actually false. This is only delta G can tell us this, okay? False. And then the last one is saying delta H, standard enthalpy, and delta S of the surroundings will always have opposite signs, and that is true. So if we have delta S of the surroundings, if we see our equation, it'll be a negative delta H standard divided by temperature. So that is always true. Okay, so all of our true ones are these ones. Okay. Okay, so for this problem, this one basically asks you to balance the equation and then asks what the coefficient of one of the compounds molecules are. Okay, so the first thing I would do is break these down into half reactions. Fe2O3 turns into Fe, and then CO2. Okay, so the first thing you want to do is always balance out the atoms that are not oxygen or hydrogen, in this case iron. So I'm going to add a 2 here for the iron. And we're good with the carbon down below. The next thing I'm going to want to do is balance out the oxygens. So here on the top, I'm missing a few oxygens. I'm missing 3 oxygens. So the way I'm going to fix that is by adding 3 water, okay? Because water contains oxygen, and then by having 3 waters, we have 3 oxygen. Okay, but what I've done here is create too many hydrogens than the left side, right? We always want them to be balanced, and so the way I fix that is by adding 6 hydrogen on the left side, since we have 6 hydrogen on the right side. Okay, so now I've created another imbalance with charge, right? We have a net charge here of +6 and a net charge on the right side of 0. So we want those to be the same, okay? The way to fix that is by adding 6 electrons there, okay? And that will neutralize the charge. Similarly, on the bottom reaction, first thing we need to do is fix our oxygen. So I'm going to just add 1 water. And then I need to balance out those hydrogens again. So I'm going to add 2 hydrogen. And then we need to fix those charges once again. And so I'm just going to add 2 electrons to fix that. Now that I want to combine everything together into one balanced reaction, I'm going to multiply this by 3, okay? And so what that will give me, I'll rewrite it here. Our goal is always to cross out our electrons, so we can do that now. We can also cross out our hydrogens and we're left with a combined, I'll write it on top, Fe2O3 plus 3CO. So everything on the right stays on the right again. Oh, we also crossed off our water. Okay. So this will be our final equation. And the question was asking what is the coefficient of CO? And in this case, it is 3. So the answer is 3 here. The next problem is a review problem. We're just ranking our acids and bases again. So I'm going to label them. This is a strong base. This is a strong acid. This is a weak acid. This is neutral. This is a basic salt. So I'm just going to say weak base. Same with this one, also a weak base because it's a basic salt. So I'm just going to put that roughly in the order that I think it should go in from what I know. I know that my strong acid needs to be on top, so HNO3. We only have one other acid, so that's the only one that can go below it. And then we have like a neutral one, NaCl. And I know my strong base needs to go all the way at the bottom, right? So all that we're left to do is fill out these two spots here with these two. We just need to figure out which one's more acidic, which one's more basic. All we need to do is reference our Ka table and see which one is slightly more acidic than the other, right? Because this is a low pH, this is high pH. Okay. And so what you find is this is going to go here. Okay, and so this ends up being number 4, which is what the question was asking. Which one is number 4? So it is this one. Okay. Number 6 is asking to choose the best pair of compounds that buffer around pH of 4. A buffer range is plus or minus 1 pH. And all we need to do is find all the pKa's, okay? And for the first one, the pKa is 3.14. The second one, it's like around 9. The third one, these are kind of like salts, and so they kind of completely cancel out and don't really give us a buffer. And the last one has strong species, and so we can't really create a buffer system that way, especially without enough information. And so what ends up being the case is this is going to be our answer, since this is close enough in our buffer range of 1 plus or minus 1 pH. Number 7, it's just asking the cell potentials. So all we need to do is take 1.5 and find the difference between these. So we're going to do minus 0.954. And so that will give us an answer of 0.546 volts. Number 8 is asking, how do we increase the amount of work in a system? And if you remember the review session, in a system, the way to increase the work is by increasing delta G. We want delta G to be more positive. We want it to increase. Not decrease, not become more spontaneous, become less spontaneous. So the way to do that is by driving this reaction backward, okay? Using Le Chatelier's principle, we want to drive it backwards. And so the way to do that is by adding H3O+, adding more reactants or more products here to drive it toward the reactant side. And then another way, let's see, adding F minus, yes. And then C would be removing F minus, so that would not help. Or removing HF, that would help. Driving equilibrium the other way. That might not be the best way to describe it. Basically, driving the reaction toward the left. Is what we want. If we did add NaOH to the reaction, it would drive it to the right, okay? It would drive it to the right because because it would be a better base than water and react with HF, which is a weak acid, which is not what we want. We don't want it to go forward. We want it to go backward. Okay. So number 9 is a conceptual question about galvanic cells and stuff like that, so electrochem. And so the first statement is, first let's kind of break down what's going on here. So I'm going to label which one's the anode and cathode. So the one, the lower SRP is the anode. So here we're going to be experiencing oxidation, and this one's going to be the cathode, experiencing reduction. And if I kind of draw out a little bit what's going on here, always helps to draw it out. Okay, so this one's going to be flipped because it's the anode. We flip that one. We flip the lower one. So if it's the anode, it's going to be over here. Okay, so in this case, the anode is being oxidized, and so that means it's turning into the aqueous form. However, on the cathode side, the opposite is happening. It's being reduced and turning into the solid form. Okay, so this anode is going to be losing mass because the Fe is going to be oxidized, turns into the Fe3+, which is increasing in concentration. While on the other hand, on the cathode side, the Au3+ is turning into the solid Au. So the solid gold Au is gaining mass, while the Au in concentration, the aqueous, is losing concentration. Okay. So the first statement is saying electrons will go from the gold, the cathode, to the solution down here, and that is false. It's going the opposite way. It's going from the anode to the cathode, not the cathode to the anode. So electrons are going that way. Iron is the metal at the anode. That is true. True. C is cations will flow to the iron metal side. So I forgot to draw my my salt bridge here. So in my salt bridge, we see the anions going toward the anode, okay, and we see our cations going toward the cathode side, okay. So the question is saying cations will flow to the iron metal side? No, only anions will. Okay. If platinum is as an inner electrode will be added to the cathode side, will it change the potential of the cell? This one is saying it won't change the potential of the cell. That is true. And then the flip side is false, okay? So if you added it, oh, sorry, I don't know why I wrote it like that. So if you add platinum here, like I was saying in my review session, it has no problem transferring those electrons through, letting that Au turn into solid gold, and letting that solid gold accumulate on the platinum electrode. However, platinum has a big problem when you put it on the anode side because it doesn't want to erode, it doesn't want to react, it's not going to turn into Fe3+, you know what I'm saying? And so that will drastically affect the cell potential if we put the platinum on the anode side, okay? It doesn't like it doesn't like it because it's inert, that quality that it does not like to react with things. Okay, so therefore if we add it to the cathode side, it won't change the potential, but if we add it to the anode side, it will, okay? So that's why E is false. And then it's saying, F is saying iron is the oxidizing agent, okay? So oxidizing agent means it undergoes reduction, okay? That is not what we see here. Iron here is undergoing oxidation, therefore is the reduction reducing agent. Okay, so that's going to be false. Okay. G is saying the salt bridge allows electrons to, that's already wrong. So it's, the salt bridge doesn't transfer electrons anywhere. Okay, that's not what's going on there. The only thing that transfers electrons is this wire on top. The salt bridge, only anions, cations, that's it, only ions, not electrons. Okay. Number 10 is saying, what is the standard line notation for the galvanic cell where this reaction occurs? And okay, let's break this down. The first thing I'm going to do is take these apart into half reactions and break down what's going on. So we're going to have Cu turns into Cu plus. All we need to do is add 1 electron, and that's finished. The other half reaction is not so easy. So, okay, so we have those, and we have a lot of fixing up to do. So first thing I notice, we need more oxygens on the right side. So I'm going to add some water. I'm going to add 2 water because we're missing 2 oxygen. Okay, now we have an imbalance of hydrogen. We're going to fix that. Okay. And now we have an imbalance of charge. We have a net charge, a net plus 3 charge on the left, 0 charge on the right. And so I'm just going to add 3 electrons to fix that. Okay. So basically all we need to do, we can like balance this equation and then put it all together. We can actually try that. Okay, at this point, these would cancel out, but that's pretty much it. And so when you put everything together, you're still going to have this H plus remaining. Okay, even though we didn't see it over here, it's really important. Okay, so when we're deciding what our line notation is, we have to consider a lot of things. First, let's figure out what the anode is. Okay, so the anode is the one that undergoes oxidation. Okay, so the one that's being oxidized right here, let's see, is the copper. Okay, so we're going from a copper solid with a charge of 0, and then it's ending up here with a plus charge, which means it lost an electron. Okay, so we know for sure the copper has to be the anode. Okay, so copper anode. That must mean that the NO3 is at the cathode side. Okay, the NO3 and the NO is at the cathode side. They're both aqueous, so that also causes a problem. So I'm going to look over here. And I'm going to see which ones show copper at the anode side, okay? All these ones are wrong because copper is not the anode, okay? B is wrong because I don't know where this plus 3 came from. That is not what we're dealing with. So we're between A and F at this point, okay? Our platinum is at the cathode solid side because we don't have any aqueous. We don't have any solid electrode at the cathode side, only aqueous, okay? But the question then lies in, should we include this hydrogen or not? That's the only difference between A and F. And the answer is yes. So the answer is going to be F. We do need to consider the HF, but then why don't we consider water? Well, water is always around, right? Water is the solvents that we use everything in, so we don't include water, even though we did see water over there, right? Okay. For 11, this question is just asking, when are metallic compounds in their ionic form? This might seem like a tricky question, but it's super simple. You can also reference my review session. So basically, when you're looking at molecules, if you look at the chart, the SRP chart, molecules that have like a negative SRP, like aluminum, so Al 3 plus 3 plus 2 Al. So this one has a negative 1.66 SRP. Okay. We always flip these, right? We always flip the half reactions that have negative SRPs. So we're going to flip this around. Okay, this represents how this reaction wants to go. Okay, this reaction wants to go this way. It wants to go from this solid form of aluminum to the aqueous form, or the ionic form. Okay, ionic. Ionic, again, just means it has a charge. So any compound that has a negative SRP will prefer the ionic form at equilibrium. Okay, so the answers are here. You can look at your equation sheet as well. Okay, so for number 12, this is a little bit longer of a problem. So for this, the first thing I'm going to do is look at delta G. So I want to find what the total delta G will be of the reaction. So I'll do products minus reactants. And that will give me negative 4.3. Okay. And then, okay. And then the next thing you're going to want to do is take a look at what we're given here. So I'm going to write a little ice table. So A just turns to B, and we know what our initials are. So 1.45, 0.789. Okay. So we know what our initials are, and we're going to go through some change. Okay. And as we know, delta G standard equals negative RT ln of K. And what is K? K is just products over reactants at equilibrium. So we're going to do our products, 0.789 plus X, over our reactants. Great. Okay. So we have the temperature, which is 284. And we have our R constant, 0.008314. And we can solve for X, okay? Because we also have delta G here, which we just found, which is 4.3. Negative 4.3, sorry. Okay. So once you calculate X, you should get 1.138. Okay, but that's not answering the question entirely. We want to find out what is our final B concentration. So we're going to do 1.138 plus 0.789, and that will give us a total of 1.927. Okay. Okay, 13, we're doing something similar, but a little bit extra steps. So we have, let's set up another ice table. We have B, A, 2A goes to B. We have our initials, 1 molar, 0 molar. We have some change. Our change is going to be 2x this time because we have a 2 coefficient here. Okay. And we're going to end up with some result down there. Here's just going to be plus 1x because we have one coefficient. Okay, so it tells us at equilibrium, the concentration of A changes by this amount. Okay, it doesn't say this is the end amount. It says this is how much it changes by. That means 2x is equal to 0.56. Okay, so that means that x is equal to half of that. So, which would be 0.28. Okay. So if we were to solve this, all we need to do is just some math. So this would be 0.44. This would be 0.28. Okay. So then we can use this information and we can find, because this will tell us at equilibrium, we can find out what happens with delta G standard. So delta G standard equals negative RT ln of K. So K is just going to be 0.28 over 0.44 squared, okay, squared, because of that coefficient that we were dealing with before, okay? So you're going to solve for delta G, and that will equal negative 0.81, okay? But we're not done yet. We need to find what delta G non-standard is at this certain concentration. So let's do another ice table. So A goes to B, and so we know we have the same initials. We have some change, but we know we end with 0.35 down here, okay? The only way we could have gotten that is by adding 0.35. And because we have this, 2x relationship here, that means that the change of B needs to be double the change in A. So it's going to be 0.7 change, and our final will be 0.3 molar. We can add these into Q, okay? This will help us find Q, which is the relationship not at equilibrium. So let's write this down here. Delta G non-standard equals negative 0.81 plus RT times ln of Q. And this time Q is going to be 0.35 divided by 0.3 squared, okay? Always going to keep that squared there. And then once you solve for delta G non-standard, this will equal 2.18 kilojoules, okay? That'll be your final answer. Okay. 14 is asking about what happens in this cell conceptually. So if we were to have a similar cell as always, we know this is going to be the anode because it has a lower SRP. So we know that there's going to be iron here. Okay. So basically what's going on here, the anode will oxidize, so the iron will turn into Fe3+. So the iron solid will lose mass, okay? While on the other side, this Au, this gold, will gain mass as Au3+ reduces and turns into its solid form of Au, okay? So the statement A is saying the concentration of Au3+ will increase, okay? That is false. It will decrease, okay? Because it is turning into the solid form of AU or gold. For B, it's saying the concentration of Fe3 plus will increase, and that is true. As the solid iron will oxidize, it turns into that Fe3 plus, increasing that concentration there. The next one is saying the mass of the gold will increase, and that's absolutely true. This will accumulate here as the Au3 plus is being reduced and turning into it. The last one is saying the mass of Fe will decrease, and that is also true. We're going to be eroding here. It's going to be eroding as the Fe oxidizes and turns into its aqueous form. 15 is asking just about the cell potential once again. You don't have to worry too much about what's going on here. Just look at the SRPs or the, so all you need to do here is take the lower value and like flip it, or what you can do is just find the difference between the two. So you'll do 1.68 minus 1.51, and you should get D. Okay, so that's pretty much everything. You guys feel free to email me if you guys have any questions for sure.